Assalamu alaikum students. In today's lecture we will discuss some basic and important concepts related to communication. We start with noise, interference and distortion. Noise is a random and undesirable signal that enters into the communication system through the communication medium and interferes with the transmitted message signal. So looking here, we have the graphical representation of a typical noise. Okay, so you can see here that this noise signal varies randomly. Okay, so you can see the magnitude of this noise signal varies very randomly. Okay. Then we have interference. So interference is another phenomena which cause contamination to the transmitted signal, and this contamination basically occurs from the transmission of external sources. Okay, so interference is more severe in case of radio communication systems. In fact, in radio communication systems, the transmitted signal travels through the air from the transmitter to the receiver. Okay, so for example, if we have a transmitter receiver pair, okay, and if the transmitter transmit a particular signal to a particular receiver, okay, then the receiver antenna not only receives the signal which is intended for it, but it also receives the signals transmitted by other transmitter to other receivers. So those signals which are not intended to the receiver, but the receiver receives them, so they cause interference. Okay. Similarly, we have distortion. Okay, so distortion is basically the perturbation or the disturbance caused to the signal. Okay, so for example, if you transmit a signal and when the signal passes through the channel, so due to the channel, the shape of the signal may be changed. Similarly, the signal may be spread in frequency domain or in time domain and so on. Okay, it may also happen that the circuitry of the transmitter or the circuitry of the receiver cause distortion. Okay, so in order to remove the effect of distortion, equalizers are used. Okay, so in communication, noise is unavoidable. Okay, and it will contaminate the transmitted signal along the path from the transmitter to the receiver. Okay, there are then two types of noise in communication. One is internal noise. This internal noise is caused by the internal devices or components in the electronic circuit of the transmitter and the receiver. Okay. Similarly, we have external noise. The external noise occurs due to the channel, okay, or due to the interference caused from the outside, or some natural noise like cosmic noise and so on. Okay. So in general, noise is one of the basic factors that limits the performance of communication system. Okay. Generally, in communication, we assume that the communication channel are additive noise channel. It means that if we have, for example, a communication channel, okay, and if the message signal S of t is transmitted through this channel from the transmitter to the receiver, then during the transmission, noise will enter into the signal. Okay. Now, in case of additive noise channel, we assume that the noise N of t is simply added with this signal S of t, and at the receiver, the received signal R of t will be simply equal to S of t plus N of t. Okay. So if we have such type of channels in which the noise is simply added to the message signal, and then at the receiver we have this summation, then these type of channels are called as additive noise channel. So additive means that this noise N of t is simply added with the message signal. So you can see here that the noise signal N of t is not multiplied with the message signal, neither the message signal is divided by the noise, but the noise is simply added to it. Okay. So it may also happen that when the signal travels through this channel, the magnitude of this signal is also attenuated. So the magnitude of this signal is attenuated, and then this noise is added. So in such scenarios, the received signal R of t will be equal to A into S of t plus N of t, where this A represents the attenuation factor. Okay. So here we see the performance metrics used in communication. Okay. So for analog communication, the performance metric used is signal to noise ratio. Okay. Signal to noise ratio is generally represented by SNR, which is equal to signal power divided by noise power. So that's why we call it signal to noise ratio. It is the ratio of the signal power to the noise power. Okay. So if we have an analog communication, and if the SNR at the receiver end is high, then we say that this analog communication has good performance. Okay. If the SNR at the receiver is low, then we say that the performance of the analog communication is not good. So it means that if we want to have a good communication system with high SNR, then we should either increase the signal power or decrease the noise power. So the SNR will increase by increasing the signal power or decreasing the noise power. Okay. In case of digital communication, we have bit error probability, which is used as the performance metric. Okay. So bit error probability is the probability that a received bit at the receiver has been altered due to noise, interference, distortion, or bit synchronization error. For example, if we have a communication system, okay, and in that communication system we transmit a positive pulse for a binary 1, and similarly we transmit a negative pulse for a binary 0. Okay. So for example, now if we have transmitted a binary 1, so it means that we have transmitted a positive pulse. Okay. So now during communication, if due to the noise, interference, or distortion, this positive pulse has been changed to a negative one, then at the receiver will receive a negative pulse. Okay. And after reception of this negative pulse, the receiver will decide that the transmitted signal is a 0, and which was basically 1. Okay. So now if we have a communication system in which this type of error is high, then that communication system will be bad. If this type of error is small, then that communication system will be good. Okay. So now what happens? This error basically depends on noise, interference, and distortion, etc. Okay. Now noise, interference, distortion, all these things are random. Okay. Now this random nature of noise, interference, and distortion, we see the probability that a bit will be in error. Okay. So if we have a system where the probability of bit error is high, then that system will be bad. And if we have a system with low bit error probability, then that system will be good. Okay. So here we have the electromagnetic spectrum. This is the electromagnetic spectrum, which is divided to different bands. Okay. So here from 300 Hz to 30 kilohertz, this range is called as very low frequency band. Then from 3 kilohertz to this range here, this is called as the low frequency. From here to 3 megahertz, this is the medium frequency, and so on. So here we have EHF, so this is called as the extra high frequency. Here we have infrared, here we have the visible light band, and finally here we have the ultraviolet light band. Okay. So for different communication, different bands are used. For example, the twisted pair cable communication, which is used in landline telephony. So the landline telephone cables are called as the twisted pair cables. So in these cables, the communication is performed in this range here, in very low frequency range. Similarly, looking here, for example, infrared. So in case of remote, we use remote for changing, for example, the channels on TV. So these remotes are using infrared. Okay, and similarly, infrareds are also used in sensors and other devices. Okay, similarly, optical communication or optical transmission is taken in this part of the electromagnetic spectrum, which is the visible light part of the spectrum. Okay. So now we see what is frequency spectrum and what is bandwidth. Okay, so for example, if we have a signal or a waveform, okay, that signal or waveform will contain a number of frequencies. Okay, so we will have a highest frequency, then there will be a lowest frequency, and in between we will have other frequencies. Okay, so it means that we will have a range of frequencies in each signal. Okay, now the total frequencies in a waveform or in a signal is called as the frequency spectrum of that waveform or that signal. Okay. Similarly, the bandwidth of frequency spectrum is the range of frequencies contained in the spectrum. For example, if we have a spectrum, this spectrum contains a number of frequencies where the highest frequency is represented by f of h and the lowest frequency is represented by f of l. Okay, and in between we have other frequencies. Then the bandwidth of this frequency spectrum BW will be equal to f of h minus f of l. Okay. Similarly, if we have a signal x of t and that signal has a number of frequencies inside it, then the bandwidth of this signal will be equal to the difference between the highest and the lowest frequency contained in this signal. Okay, so for example, looking here, if we have x of t, then the Fourier transform of x of t will be equal to capital X of f. Here this capital X of absolute represents the magnitude of the Fourier transform of x of t. Okay. So now in this X of f absolute, we have a number of frequencies. Okay, so on this side we have positive frequencies, here we have negative frequencies. So remember that this part where we have negative frequencies is just for mathematical representation. Okay, so in practice we don't have negative frequencies, we only have positive frequencies. So this part occurs due to the symmetry property of the Fourier transform. Okay, so in real sense we can say that in this X of f we have the lowest frequency is equal to 0 and the highest frequency here is equal to fm. Okay, so the bandwidth of this X of t from here can be obtained to be fm minus 0, which is equal to fm. Okay. Similarly, different communication channels have different properties. Okay, so for example, some channels will allow one set of frequencies while the other channel will allow different set of frequencies. Okay, so for example, if we have communication channel and this communication channel allows a certain range of frequencies and blocks the remaining frequencies. Okay, then for this communication channel the bandwidth will be equal to the difference between the highest and the lowest frequency that this channel allows to pass through it. Okay. So here we have pulse code modulation. Okay, so this is another concept. Okay, so for example, if we have 0, this is a 0 digit, it is represented by a binary equivalent 0 0 0 0. Okay, similarly we can see here 7 is a digit, and this digit in binary form is given by 0 1 1, and similarly 15 is represented by 1 1 1 1. Okay, so now pulse code modulation is a technique that assigns codes to the binary digits. Okay, so for example, if we select a pulse code modulation technique in which we will assign a negative pulse to 0 and a positive pulse to 1, okay, then looking here for this 0 0 0 0 we have these 4 negative pulses. Okay, similarly looking here for these 4 ones we have 4 positive pulses. Okay, and for example, if we see 10, which is represented by 1 0 1 0, then for this 1 we have a positive pulse here, for 0 we have a negative pulse, similarly again we have 1, so we have another positive pulse, then we have a 0, so we have a negative pulse here. Okay, so now this process in which waveforms are assigned to bits is called as the pulse code modulation, and these waveforms are called as the pulse code waveforms. Okay, so now we see analog to digital conversion. Okay, for example, if we have an analog signal and we want to transmit it through a digital communication system, then the first step will be to convert this analog signal to a digital signal. Okay, majorly analog to digital conversion involve these three major steps, which is sampling, quantization, and coding. Okay, so sampling basically is the process in which samples of this analog signals are taken at equal interval of time. Okay, so looking here, for example, we have taken one sample at time t is equal to 0, then at time capital T another sample is taken. Okay, then at time equal to 2n to capital T this third sample is taken, and so on. Okay, here you can see that the time duration between two consecutive, for example between these two pulses or these two pulses, is the same. So here the time difference or the interval is equal to capital T. Here also the interval is equal to capital T. Or you can see, for example, here if we see this sample and this sample, again the difference, the time difference between these two samples is equal to capital T. Okay, now this sampling interval capital T is called as the sampling period. Okay, and f of s, which is equal to 1 over capital T, is called as the sampling frequency. Okay, so f of s is equal to the number of samples per second. Okay, so this is sampling. Okay, and the next step is to perform quantization. Okay, quantization basically is a process in which these samples are approximated to nearest quantization level. Okay, so in quantization, first this vertical axis is divided into a number of equal intervals. Okay, so in this case here we have 8 intervals. Okay, and the height of each interval here is equal to 1. Okay, so for example here we have 0, then this height is equal to 1, then this height here is equal to 2, then this is 3, 4, 5, 6 and 7. Okay, so now each of these samples are approximated to the nearest quantization level. Okay, so you can see here this first sample here is quantized to this level number 5, whose height is equal to 4. Similarly, the second sample is approximated to 6th level, okay, 7th level, sorry, whose value is equal to 6. Okay, so the height here is equal to 6. And similarly, this sample here, which occurs at 4 and to capital T, is approximated to this second level here, whose value is equal to 1. Okay, so now this process is called as quantization. The next step is to represent each of these levels in binary form. Okay, so now looking here, this is 5th level. The value of this 5th level is equal to 4, and 4 in binary form is equal to 1, 0, 0. Similarly, here this is the 7th level. Its value is equal to 6, which is represented by 1, 1, 0. Okay, and so on. Okay, so remember here that these quantized level here are the approximation of this original sampled signal. Okay, you can see here that the level here, the sample here at 40 is less than 1. Okay, so if you see here, the value is below 1, but here it is approximated by 1. Okay, so the nearest quantization level to this sample is 1. Okay, so that's why it is approximated by 1. Okay, similarly, you can see here that the sample here at 5t is greater than 1, but again the nearest quantization level to this sample is 1. So again here we have approximated this sample to 1. Okay, so the next step is coding or pulse code modulation. Okay, so here these codes here are assigned with waveforms. So for example, this first sample whose value is 4 and which is represented in binary form by 100, it is shown by these 3 pulses here from here to here. Okay, so you can see here that 1 is represented by a positive pulse, then we have 0, so 0 is represented by a negative pulse from here to here, then again we have a 0, so this 0 is represented by another negative pulse which is from here to here. Okay, similarly the second sample here whose value is equal to 6, in binary form it is equal to 110, and this 110 is also represented by 3 pulses here. Okay, so now this part here 110, this represents the second pulse. Okay, so for 1 we have a positive pulse from here to here, then for 1 we have another positive pulse from here to here, then for 0 we have this negative pulse, and so on. Okay, so in this way, from this analog signal we have arrived to this digital waveform. Okay. Okay, now we will see the importance of signal to noise ratio and bandwidth of communication system. Okay, so in communication system we have 2 primary resources. One is power. So power is used to energize the transmitter and receiver circuits. Okay, and similarly it is also used to transmit the wireless signal as an electromagnetic wave. Okay, and then we have the channel bandwidth. Channel bandwidth is the range of frequencies which the channel allows to pass through it. Okay, so both power and channel bandwidth are very important. Okay, so and particularly channel bandwidth is very scarce and it is very expensive. Okay, the reason is that generally we have a number of communication services, similarly we have a number of communication devices. Okay, and as the number of communication services and devices increase, the requirement of the bandwidth increases. Okay, and due to this reason the bandwidth or the channel bandwidth becomes expensive. Okay, though both these resources, power and channel bandwidth, they both are very important. Okay, but in some scenarios one of these resources may be more important than the other. For example, if we have deep space communication, okay, like if for example we have satellite communication. Okay, so in case of satellite communication, the bandwidth is not that important as the power is important. Okay, so because we need a lot of power to be transmitted. Okay, so in such scenarios the communication is called as power limited communication or power limited scenario. Okay, similarly in cellular communication power is not that issue because the transmitter and receiver, they are not far apart from each other. Okay, but because of the large number of cellular services and large number of cellular users, there is a competition for bandwidth. Okay, and that's why in such scenarios bandwidth is very important compared to the power, and such type of communications in which bandwidth is more important are called as bandwidth limited communications. Okay, so now looking to the SNR and bandwidth of communication system, the objective of any communication engineer will be to design a system which transmits the message efficiently, reliably, and fulfills the constraints on power, bandwidth and cost. Okay, so it means that any communication engineer will try to design such a system which is power, bandwidth and cost efficient, and similarly it transmits the required information reliably. Okay, so basically efficiency is measured as the amount of message sent in unit power, unit time and unit bandwidth. Okay, so if you transmit more information in less power and less time or in less bandwidth, then the communication will be more efficient. And similarly, if you transmit less amount of information in unit power, unit time and unit bandwidth, then the communication system will be less efficient. Okay, reliability is something which deals with the accurate transmission of the information signal. Okay, so if for example we have a communication system in which the transmitted signal is corrupted by noise, interference and channel distortion, and then the signal arrived at the receiver will be different from the one transmitted by the transmitter, and such type of communication will be non-reliable communication. Okay, so in case of analog communication, reliability is expressed in terms of SNR. Okay, so in case of analog communication, if the SNR is high, then the communication will be good. Similarly, in case of digital communication, the probability of error is used to express the reliability. So if the probability of error is small, it means that small number of bits will be in error. Okay, and such type of communication has high reliability. Okay. Now we come to another concept which is very important in digital communication, and this is the channel capacity and data rate. Okay, so first we need to know about the data rate and the channel capacity. Okay, so data rate represents the number of bits per second transmitted. Okay, so if we have a system in which we transmit, for example, R number of bits per second, then the data rate will be equal to R. Okay, so this is the number of bits transmitted per second, where channel capacity represents the number of bits per second which can be successfully transmitted over a communication channel. Means that successful means that without error or with zero error. Okay, so for example, if we have a digital communication system, and that communication system we have a channel. Okay, now this channel has a certain capacity, means that it allows a known number of bits per second to pass through it and arrive at the receiver with zero error. Okay, if the number of bits transmitted per second increases that value, the channel capacity, then there will be error at the receiver. Means that the signal can be transmitted to the channel, but due to the limitation of the channel, the arrived signal will be having errors. Okay, so the channel capacity is represented by a very famous formula which is called as Shannon capacity formula, and this formula is given here. C equal to B and to log of 1 plus SNR, where B is the bandwidth of the channel and SNR represents the signal to noise ratio at the receiver. Okay, so if we have a channel with bandwidth B and signal to noise ratio SNR given, okay, then the maximum number of bits per second that can be transmitted through this channel without error will be equal to C. It means that in such channel, the number of bits transmitted per second cannot exceed C. Okay, so this is a value here. Always the number of bits transmitted per second in this channel should be equal to or less than this value. Okay, so looking here, you can see this curve represents C. Okay, so with changing signal to noise ratio here, this capacity also changes. Okay, so this is C. Now if the data rate, which is the number of bits transmitted through this channel, is represented by R. Okay, so if R is equal to C, it means that the number of bits transmitted through this channel is R, and R is equal to C, then we can transmit these bits without an error. Okay, if R is less than C, the number of bits per second transmitted through this channel is less than C, then again there will be no error. And if it happens that the number of bits per second R which is transmitted through this channel is greater than C, okay, then there will be an error, and this part here is called as the unattainable. Okay, so data rate should always be less than or equal to channel capacity. Data rate cannot exceed the channel capacity. If we increase the value of data rate from the channel capacity, then at the receiver we will have errors in the communication. Okay, so this is also called as the upper bound. This blue line here, blue curve, is also called as the upper bound on the channel capacity. Means that this shows us the limit of the channel capacity. Okay, so now coming back to this formula here, in this formula we have bandwidth B and SNR R. Okay, so if we want to increase the channel capacity, then we need to increase the bandwidth of the channel or the SNR of the channel. Okay, so in some scenarios we can enhance the capacity of the channel by increasing the signal to noise ratio, and similarly if the signal to noise ratio is fixed, then by increasing the value of B, which is the bandwidth of the channel capacity can be increased. Okay, so generally this formula provides us a basis for the trade-off between bandwidth and SNR. Okay, so the next concept is multiplexing. Multiplexing is a technique which is used for the simultaneous transmission of multiple signals. So here we have two major types of multiplexing. One is frequency division multiplexing and the other is time division multiplexing. Here in this slide we will explain frequency division multiplexing in detail. Now look here, we have three signals, signal 1, signal 2 and signal 3. All of these three signals are shown in frequency domain. Okay, so the horizontal axis shows the frequency. Okay, so now you can see here that the bandwidth of all of these three signals is the same. Okay, so the bandwidth ranges from 330 Hertz to 3200. Okay, now our objective is to transmit these signals simultaneously. Okay, if we transmit these signals simultaneously in this form and the same channel, okay, then what will happen? These signal will interfere with each other and we will have a composite signal containing signal 1, signal 2, signal 3 and they will be mixed together. Okay, so at the receiver we will not be able to remove signal 1, signal 2 and signal 3. Okay, so multiplexing is the solution for such type of scenarios. So in multiplexing what we do, we divide the spectrum into a number of bands. Okay, so here we have one band which is from 60 to 80, then we have another band from 80 to 100 and the third band ranges from 100 to 120. Okay, so now from 60 to 80 this is one channel, then from 80 to 100 this is another channel, and from 100 to 120 this is another channel. Okay, so in multiplexing what will we do? We will transmit signal 1 in this channel whose frequency range is from 60 to 80, then the signal 2 will be transmitted in the second channel whose range is from 80 to 100, and signal number 3 will be transmitted in the third channel whose frequency ranges from 100 to 120. Okay, now this signal is called as the multiplex signal, and here all the signals are transmitted separately, so they are not mixing with each other. Okay, and at the receiver this signal 1, signal 2 and signal 3 can be separately received. Okay, now we see another concept, modulation. Okay, modulation is very important both in analog as well as in digital communication. Okay, modulation basically involves two signals, a message signal and a carrier signal. So generally message signal are low frequency signals, while the carrier signal is a high frequency sinusoidal wave. Okay, so it may be a cosine or a sine wave. Okay, so in modulation the message signal modifies the characteristics of the carrier signals. Okay, and then that modified carrier is transmitted. Okay, so the modified carrier is called as the modulated signal, while the message signal is called as the modulating signal. Okay, and this process is called as modulation. Okay, so there are several types of modulation schemes. For example, amplitude modulation. In amplitude modulation, the amplitude of the carrier signal is modified with respect to the message signal. Okay, the counterpart of this amplitude modulation for digital communication is amplitude shift keying. So amplitude modulation is analog modulation, while amplitude shift keying is digital modulation. Okay, similarly we have frequency modulation. In frequency modulation, the frequency of the carrier is modified with respect to the message signal. Okay, and in digital case frequency modulation is called as frequency shift keying. Okay, similarly we have phase modulation. Okay, so in phase modulation the phase of the carrier signal is modified by the message signal, and then that carrier with modified phase is transmitted. Okay, and digital communication phase modulation is called as phase shift keying. Okay, so let us see how amplitude modulation works. Okay, so for example this is an analog data, okay, or analog message. Here we have a carrier. This is a sinusoidal carrier, cosine signal, okay. So in analog communication, the magnitude of this carrier changes with respect to the amplitude of the data, okay. So you can see here that as the magnitude of this analog signal is increasing, here the magnitude of the carrier also increases, okay. At this point the amplitude of the signal is 0, so here we have 0, okay, and so on, okay. So here this signal now is called as amplitude modulated signal, and this signal, the amplitude of the carrier now changes with respect to the message signal, this one, okay. So then we have frequency modulation. So again here we have a message signal, here we have a carrier signal. Again this carrier signal is a sinusoidal signal, a cosine signal, okay. So here the frequency of this carrier signal changes with respect to the changes in the message signal. So here in this region the magnitude of this message signal is high, okay. So the frequency of the carrier signal is increased. Similarly in this region the message is negative, small, so the frequency is also decreased, okay. So in this way in frequency modulation the frequency of this carrier increases or decreases with increase or decrease in this message signal, okay. And here this signal is called as the frequency modulated signal, okay. And finally we have phase modulation or phase shift keying, okay. So for example here for demonstration I have chosen phase shift keying, which is digital modulation technique, okay. So in analog case we call it phase modulation, while in case of digital communication we call it phase shift keying. So here we have a carrier, again a cosine or sinusoidal carrier. Here we have this data in the form of pulses to be transmitted. So now looking here, from here to here the value of the pulse is negative, and here the value of the pulse is positive, then negative and negative. So for this region we transmit this carrier, okay. So from here the pulse changes to positive, so from here to here we have positive pulse. So at this point when we go from 0 to 1, the phase of the carrier changes, so we have 180 degree phase shift, okay. So from here to here we have this carrier, then now again at this point the signal changes from 1 to 0, so again the phase of the carrier changes, and again we have 180 degree phase shift, okay, and so on. So now looking here, from here to here there is no change in the signal, so we have no change in the phase in this region, you can see, okay. So now this was just for introduction to modulation, and you shouldn't worry if you don't understand the things properly, because modulation schemes, analog as well as digital, will be covered in detail in the upcoming chapters. So this was just for introductory purposes. So demodulation is the reverse process of modulation, okay. So for example, looking here, this is an amplitude modulated signal, okay. When this signal is transmitted and this signal arrives at the receiver, we need to retrieve this message signal back from this modulated signal, okay. Similarly, if we receive this frequency modulated signal at the receiver, then we need to retrieve this message signal back from it, and so on, okay. So in order to get the message signal back from the modulated signal, we need to do demodulation, okay. So the demodulation process converts the modulated signal back to its original message signal, okay. So here we will see that why modulation is needed, okay. So why we do modulation, why don't we transmit the message signal directly, okay. So there are several reasons, okay. In fact, in radio communication we need an antenna, okay, and the size of antenna is proportional to the wavelength of the signal, okay. In practical cases, the message signal is a low frequency signal. So when we have low frequency signal, it means that the bandwidth will be large. Okay, so if the bandwidth is large, and as the antenna height or size depends on the band wavelength, then the antenna size will also be high. Okay, therefore, in order to have a practical antenna size, we need to reduce the wavelength of the message signal. Okay, and reducing the wavelength of the message signal means that increasing its frequency. Okay, so modulation basically transforms this low frequency signal to high frequency. Okay, and when it is translated to high frequency, then the antenna size required will be practical. Okay, so the second reason for modulation is to make the transmission signal compatible with the characteristics of the transmission channel. Okay, so as we already discussed in our previous slides, that each channel has specific characteristics. Okay, each communication channel allows a certain range of frequencies while block the remaining frequencies. So if we have a channel which allows signals with a certain frequency range, then the transmitted signals should be shifted to that range which is allowed by the channel. Otherwise, we cannot transmit the signal. Okay. Now the third reason for modulation is to allow multiplexing. Okay. So look here. For example, here. Now looking here, the frequency range of this signal 1 is from 310 Hz to 3200 Hz, while it is transmitted in this channel which has a range from 60 to 80 kilohertz. Okay, so now in order to be able to transmit this signal in this frequency range, we need to translate this signal to this higher frequency range. Similarly, this signal 2 is transmitted in this range. Okay, now in order to transmit this signal 2 in this channel, we have to translate the frequencies of this signal 2 to this range. And similarly, the frequencies of this signal 3 are translated to this region, which ranges from 100 to 120 kilohertz. Okay, so now the translation of these three signals to different frequency ranges is only possible by doing modulation. Okay, so looking here, we have 60 kilohertz, then we have 80 kilohertz. In between here, we have 70 kilohertz. Okay, so now by taking a carrier of 70 kilohertz and then modulating that carrier with signal 1, this signal 1 will be translated to this frequency range. Okay, similarly, here taking another carrier having a frequency of 90 kilohertz and then modulating that carrier with signal 2, so we will get the translation of this signal 2 to this frequency range here. Okay, and here the midpoint of 100 and 120 is 110 kilohertz. So modulating 110 kilohertz carrier with signal 3, this signal 3 will be translated to this frequency range. Okay, so finally we discuss source and channel coding. So source coding and channel coding, these concepts both are used in digital communication. Okay, so source coding is also called as source encoding. Okay, and the reverse of source coding is called as source decoding. Okay, so basically source coding is used at the transmitter end, at the source end, and this is used to remove extra bits from the digital data. Okay, so if we have digital data, we have a large number of bits. Okay, so sometimes it is possible to remove some bits without affecting the overall information. Okay, so in this way the number of bits transmitted will be reduced. Okay, and in communication, if we can transmit the same information in smaller number of bits, then that communication will be efficient, because the communication will be fast, and similarly the bandwidth required will also be less. Okay, so source coding in general reduces the number of bits in the message signal. On the other hand, channel coding or channel encoding adds extra bits to the data. Okay, so this is the opposite of source coding, but source coding is necessary for the detection and removal of errors at the receiver. Okay, in channel coding, extra bits are added to the data. Okay, and this helps at the receiver end in the detection and removal of errors. Okay, like source decoding, we have channel decoding, where channel decoding is the opposite of channel coding. Okay, so we stop here. This completes our introduction to the concepts of communication systems. Okay, thank you.